Okay, so this is Unit 2.3, number 11. And in this one, you're not proving a subgroup, you're proving an equivalence relation. So in this one, they give you a subgroup, and then they define the relation. So another way of writing this, the relation A is related to B if and only if AB inverse is an H. So let's see, we can say this. The relation is A and B are related to each other, provided that AB inverse is in our subgroup of G. And so what we need to do is show that this makes an equivalence relation. Okay, so the first thing we have to do is show that our relation is reflexive. And remember what that means is that for every element, every element A in G, then A is related to itself. Okay, well, is that true? Okay, let's see. Yeah, because you can tell here, it's defined on G here. Okay, so is A related to itself? Well, let's ask ourselves this. A is related to itself if A times A inverse is in H, right? So let me write it this way. A is related to itself if A times A inverse is in H. Okay, well, any A that I pick in G times its inverse is E, right? Well, is E in H? Yeah. Why does it have to be in H? Because the identity of G has to be in H in order to be a subgroup. Because H is a subgroup of G, and so E of G must be in H as well. Okay, so we've got reflexive. Part 2, it needs to be symmetric. Okay, so if A is related to B, is B related to A? Okay, so to check that, let's start out with assuming A is related to B. Okay, well, by definition, that means that A, B inverse is in H. So what we want to show is that B, A inverse is also in H, because that would prove that B is related to A. All right, well, AB inverse is in H. Okay. What else do we know about subgroups? One of the things we know is that if something's in H, then its inverse is in H. Okay, so we also know AB inverse, its inverse has to be in H, because inverse of any element in H must also be in H. Okay, well, remember this rule, A, B inverse equals B inverse A inverse for anything in a group. If I put an inverse here, then I need to put an inverse here. And B inverse inverse is B. So this turns into B inverse inverse A inverse. Ooh. Is in H. And B inverse inverse is B. So I've got B, A inverse is in H. And that proves that B is related to A. So we've got symmetry. All right, the last one's transitive. So transitive. So if A is related to B and B is related to C, is A related to C? Okay. So we're going to start out by letting A be related to B and let B be related to C. Okay, so this tells us that AB inverse has to be an H and BC inverse has to be an H. Okay, well, the one other property about subgroups is that H is closed. So if I know this is an H and that's an H, I know their product's in H. So AB inverse times BC inverse also has to be an H. And remember, H is a subgroup, so it's got to be associative too. So this is the same thing as saying A, B inverse B, C inverse has to be an H. And B inverse B is E, and then A times E is just A, so AC inverse has to be an H. And by definition of what our relation is, that means A has to be related to C. So yes, it's transitive. So since our relation is reflexive, symmetric, and transitive, it is an equivalence relation. Why does the pen always mess up at the end? It's an equivalence relation. All right. Hope that helps.